Okay, so my screen is visible, right?
Yes, sir.
Yeah, so anything you want me to discuss or like you have any doubt?
Sir, if you can summarize, I mean, limit and continuity in short.
Okay. Okay, so limit. Again, like just like your one variable case, your here also once you know how to check how to find limit of a function, then more or less continuity also comes free. Okay, just you need to check whether that limit, if the limit exists, whether that matches with whether it matches with the value of the function at that point or not. Okay, that is the only extra part you need to do with continuity. Okay, but here the problem is checking limit. Okay, so checking limit is slightly difficult. Okay, uh, so if you don't know mm, limit, so if you have to prove limit exists, then yeah, of course you have to give a proof. And if you have to show limit doesn't exist, then you have to give a path. Okay, like two different paths in which the limit are different. Okay, so let me start with the one variable case. So suppose you have uh, a map, let's say R to R to R, right? So if you see, then this is your line. Okay, this is the domain, and this is the codomain, right? And usually you represent using you represent the graph of the function in this uh, xy plane. But again, like yeah, I can talk about so I can represent in this way. So this is a function. This basically takes R to R, right? So what you do when you check limit of a real so real variable function, that is from R to R. So what suppose you want to check the limit at, let's say, some point A on your real line. What you do? How you check the limit? Am I audible?
Yes, sir.
Yeah, how you check the limit for single variable function?
Left hand side, right hand side.
Yeah, so you check the left hand limit and the right hand limit, right?
Yes.
Yes, sir.
Right. So, and why actually you check left hand limit and right hand limit? So one of the reason is basically the domain is real. Okay, you, so there is only one way. There are only two possible ways in which you can come to this point A. Either you can come to this point A from this direction, right? Or either you can come to this point from this direction, right? There is no other possible direction through which you can come to this point A, right? So when you are approaching uh, to this point A from the left hand side, okay, so when you are approaching to this a from the left hand side, what you check, how your f of x behaves. Okay, so where this f of x approaches. Okay, that is what you check when you compute the left hand limit, right? And the next thing what you do, you check the right hand limit. So you can come to this point a from the right hand side of a. So in that case, you check the right hand limit, and you basically do the same thing. When x approaches to a plus, that is right hand limit, you basically check where this f of x approaches. So this will give you the left hand limit, the first one, x goes to a minus, and when x goes to a plus, this will give you the right hand limit. Okay, and when both left hand limit and right hand limit they matches, then you say the limit exists, right?
Yes, sir.
Yeah, so when this f of x is same as, this is your right hand limit, is same as your left hand limit, then you say your limit exists at x equal to a, right? So when you say that, so when you can say that the function is continuous at x equal to a,
So if the limit is equals to the value of the function at that point x equals to a.
correct. So if this is same as f of a, then you say that f is continuous at x equal to a, right? So yeah, so let me so I'll certainly I'll describe you this multivariable function. So before that, let me slightly recall some of the examples. Okay, so the easiest one, let's say, maybe you take a straight line, okay, or you can say some continuous, some constant function. So if I take a straight line, let's say y equal to x. So as you can see, if I pick a point, let's say this is my a. So when I'm coming to this a from the right hand side, and this is my point, let's say a comma f of a. So as you can see, when I'm coming to this a from the right hand side, then here this is coming. So here, as you can see, the value of the function is coming towards f of a. And similarly, when I'm coming to this point a from the left hand side, the value of the function is coming again towards this f of a. So that means the left hand limit and right hand limit, they are same, and they basically equals to f of a. So in that case, so this is continuous function. Limit exists and it's continuous. And if you take some, let's say, one more example, that the greatest integer function. So let's fix a domain. So define from 0 to, let's say, 2. Okay, and if I draw the graph, then this is 0. At 0, it's 0. At 1, it's 1, and in between this 0 to 1, it's 0. And then from 1 to 2, it's 2. If I fix this point 2, then at 2, it's 2. And again, like, so now you can see, if you check the limit of this function at 1, so you can see that the left hand limit is 0, right? So if you are coming to 1 from the left hand side, then the value basically it's precisely 0. So since this is 0 on this open interval, so the function is 0 on this interval. So that's why the limit is, left hand limit is 0. and uh, and also you can see that if you are coming to 1 from the right hand side, then this value of the function is 1. So that's why the right hand limit is 1, and here the left hand limit is 0 and the right hand limit is 1. So they don't match, so that's why limit doesn't exist. So as I already said, so why actually, so in real case, why actually we are checking left hand limit and right hand limit? Because we have only two directions. Okay, so when my domain is real, I have only two directions through which I can come to A. Okay, either I can come from the left hand side of A, or I can come from the right hand side of A. So that's why I have to only check left hand limit and right hand limit. But this is not true if I change my domain. So if I consider a function from R2 to R, so in that case, I cannot apply the same tree. Yeah, so if suppose I have a function, right? So suppose I have a function from R2 to R2. So that means this is my domain. So here the domain is R2, right? If I draw, so now this is my domain. So in case of R, only this line is my domain. So when I'm considering a function from R to R, this line is my domain. Okay, nothing beyond of this line is inside my domain. Okay, so here this whole plane is my domain. So my f takes this plane to some line. So this is a line, this is R, and this is my codomain. Codomain. So here the problem, now can you see the problem when I'm considering a function from R to R2 to R? So if I consider a point, suppose I want to check a limit of this function at this point. Let's say this is my point. Let's say this is my point. Suppose this is a point, A comma B. Right. So now I don't have any concept of like left hand limit and right hand limit, right?
Yes, sir, because it's entire plane.
So there are so many directions.
So many directions through which you can actually come to this point A comma B. So I can come to this point in this direction. I can come to this point in this direction. So it's not that I can come only in the form of a straight line. I can come using any some weird curve as well. So I can come like this. Okay, so this is also a path towards this AB. Okay, so I have infinitely many possible direction through which, or infinitely many possible paths through which I can reach to this A comma B. And what I have to ensure that, so it doesn't matter in which direction I am coming to AB. Okay, it doesn't matter. So when I can say that the limit, okay, so suppose I have a function from R to R, when I can say that the limit of f at a b exists. So when I can say, so basically when I can say that it doesn't matter in which direction I'm coming to AB. Okay, it doesn't matter what direction I'm taking. The value of the function will always approach to a fixed number. Okay, it doesn't matter in which direction. So if I'm taking this path, let's say this is a L1 and this is L2, this is L3. Okay, it doesn't matter in which directions. If I'm coming to this point L1 using this path AB. Okay, in that case also your whatever path you are using, this should converge to this point L. If I am using this path, in that case also this should converge to L. Okay, so whatever direction, whatever possible direction you can take, then the value of the function should approach to this number L. In that case, you can say that the limit of the function f at a comma b exists, okay, and it's equals to L. Whether the definition is clear?
Yes,
Yes,
sir.
sir.
Yes, sir.
So when actually you can say that the limit doesn't exist, so it's really easy. So if you can show that I have two different paths, so if you can show that there you have two different paths P1 and P2, okay, and both P1 and P2, they basically towards this point AB. So when you are coming to AB using two different parts, and your value of the function for this it's going towards L1, and for P2 it's going toward L2, and L1 is not equal to L2. So if you can show that there exist two paths P1 and P2, and when you are using P1 and P2 to reach this point AB, and using this path, the value of the function is approaching towards L1 and L2, and L1 and L2 are two different number. In that case, you say that the limit doesn't exist. Okay, so let me take an example. So for example, you consider this function take the easiest one, x comma y by x square plus y square, and of course if x comma y is not equal to 0 comma 0, and this is 0 if x comma y is origin, right? So this is a well defined map from R2 to R2, right?
Yes, sir.
Yes, sir.
Now this is your domain again. So as I said, it's really difficult, like in some cases actually it's really easy to guess whether the limit exists or not, but in some cases it's difficult. Okay, so for example, in this case it's really easy to tell that the limit of this function at
Well-
0 0 doesn't exist. Okay, so this is your domain. This domain is R2, and this is your codomain.
Sir,
Yes.
sir, I have to ask one thing. Like in tutorial videos, it is shown that if we try to solve it with, taking a line or some curve, which tends to 0, like let's say y equals to x, x is the line, maybe, or mx. So if we try that, and if we are getting different values in a, function, like for the limit, so it means that limit does not exist, right?
Yes. That is what I said, right? So if you can show that there exist two paths, right? P1 and P2, right? And when you are coming to this point A comma B using two paths, and for these two paths, the value of the function is approaching to two different things. Okay, in that case, you can say that the limit doesn't exist.
Sir, so I have a doubt in activity 9.4's question 8.
No, I'm not talking about now activity question. So let's focus on this part. Okay.
No, it's not doubt. Actually, like it has shown in previous two questions of that, like 6 and 7, that we have having two different values for limit, for
Uh-huh.
same limit.
Uh-huh.
And then in question number 8, when it's showing like the limit of that function does exist. and it's-
Just remind me after this question. Okay, just remind me. I just want to spend this some time on this question.
because it's not
I'll
based
come.
on same, that's why I asked.
Yeah, I'll come to that. Just let remind me after once I finish solving this question. Okay.
Sure, sir.
Yeah. So what I want to find? I want to find the limit of this function at 0, 0, right? So now there are multiple ways of coming. There are multiple ways through which I can come to this point 0, 0, right? So the probably the easiest one is, let's say, this path, right? Correct or not? And what is this path?
So it's along
Y
x-axis.
equal to 0.
Y equal
X,
to
X comma 0.
this is y equal to 0. This is basically, yeah, in some sense this is a x-axis, one side of x-axis. Okay, and x is negative, of course. Okay, so when I'm coming to this point 0, 0 using this path, and as well as x is negative here. Okay, so x is negative. Okay, so when I'm using this path, okay, so in that case, the limit is what? So limit x y tends to 0, 0, your x times y divided by x square plus y square. So as I said, I'm not using any arbitrary path. I'm using this particular path. Okay, so this path is y equal to 0. So I can replace this. So this as x y tends to 0. So in that case, I can replace x tends to 0 and y equals to 0, right? And then what I will get here?
So you're gonna put 0 wherever you see y.
0.
Yes. So in particular, I will get 0, right?
Yes, sir.
Yes,
Because the
sir.
numerator is 0.
So 0, right? So when I'm using, so when I'm coming to this point, okay, 0, 0, using this path, let's say p1, okay, my value of the function is approaching to 0, and in this case, actually, it's precisely 0. Okay, so let's take one more path. Okay, let's take this path. Okay, let's say this path. I'm coming using this path, p2. So in that case, in this case, your x is 0, right?
Yeah, x equals to 0.
And y is going towards 0. Okay, so and by the same logic, so this is the limit when I'm using the path 1. Okay. And by the same logic, what I can do here, 0, and this is same as, this is my function. Okay, sorry. X is 0 and y goes to 0. So in that case, I will get 0 and 0, right? So this I am getting using path 2, right? So as I said, these are not the only paths through which I can come to 0, right? There are infinitely many paths. So next, you consider, let's say you consider this path. Okay, you consider this path, y equals to x line. Okay, so you are coming to this point 0 comma 0 using this line y equal to x. So in that case, what you will get, limit, let's say this is my path 3. Right. So limit x comma y tends to 0 comma 0 f of x y. So if I substitute x equal to y, then what I will get? This is more or less same as saying x tends to 0 and
So x square divided by 2x square.
yes, x square divided by 2x square, and I can cancel this x square and eventually I'll get 1 by 2, right?
Yes, sir.
So this I'm from path 3, right? So okay, so maybe it's a so as you can see, when I'm using this path 1, I'm getting 0, right? And when I'm using this path 2, also I'm getting 0. Okay, but by checking just only 2 paths, I cannot conclude anything because there are infinitely many paths. Okay, but if I take this path, this line x equal to y, then I'm getting half, right? So as you can see, if you consider this path p1 and p3 for 2 different paths, you are getting 2 different limit, right? So that means the limit of the function at 0 comma 0 doesn't
exist.
exist, right? So again, like let me say it again. So by checking finitely number of paths, you can't say anything about the limit. Okay, in some sense you can't say that the limit exists. Okay, to say that limit exists, you have to give a mathematical proof, because you cannot check for all the paths because there are infinitely many paths. Okay, you cannot take all the possible path and you cannot compute the limit. Okay, for that you have to consider infinitely many cases. Okay, so for that you have to give a proof. Okay, but to show that the limit doesn't exist, that to when you want to show the limit of a function doesn't exist, in that case what you can show, you can uh, again you can take 2 paths, just like I have done for this question. You can take 2 paths p1 and p2, or here p1 and p3, and you can show that for these 2 paths the limit of the function are different. Okay, and in that and once you can show, you can find 2 paths p1 and p3 and for which limits are different. From there you can say that the limit doesn't exist. But to show to prove that limit of a function, limit of a 2 variable or 3 variable function exists, for that you have to give a proof. You can't do it by taking bunch of paths. Okay. Any doubt till now?
So, sir, basically, limit doesn't exist means we need to just prove it that it's path dependent, isn't it?
Correct. Yes.
I mean, if it doesn't exist, so path
yeah.
dependent.
So for example, like if instead of taking this line y equal to x, if I consider a general line, let's say y equal to mx, right? So this is a arbitrary line. This line is dependent on this m, right? It's dependent on the slope, right? So if you consider this thing, then you can check that this limit is basically, if you consider some arbitrary, so then
So, sir, it's getting like m by 1 plus m square, I guess.
Then in the
By taking
denominator,
this approach, we will actually be checking all the lines, right?
all the lines, yeah. But the thing is, okay, as I said, see, lines are not the only paths through which you can come to 0 comma 0, right? See, you can also you can take this path, right? And this is not a line. So maybe by considering all the lines, you can show that limit, like if you can show that the limit depends on this m, okay, then you can say that yeah, limit doesn't exist. But if you get some fixed limit for all the lines. From there, you cannot conclude anything. Okay. This is sorry, x square plus m square x square, right? And this limit is
Yes,
nothing but 1 m by 1 plus m square. And as you can see, this is completely dependent on m, right? So if I take m equal to 1, I'll get something different. For m equal to 2, I'll get something different. So the limit of this function at 0, 0 is completely depend on the slope of the line that you are taking. Okay, so that means for different lines, you will get some different limit. That means the limit doesn't exist. Clear now? Any
Yes, sir.
doubt? Any doubt from this question, or in general this concept? Okay. Okay. Someone
Yes, sir.
was asking some question. Like, can you remind me which
Sir,
question?
Yeah, activity question. Sorry, from activity 9.4,
Mhm.
question number 8. Well, you have to see 6 and 7 also for that.
Mhm.
Just check it once.
Question number
8, but for that, check 6 and 7 first.
no. What is your doubt in question number 8? Like,
So, sir, see, in question number 6, it's showing the same. It is the equation is same. So it's asking like f approaches to L as xy approaches to origin along y axis.
just a minute. Do you know in question number 8 it's asking which of the following statement are false?
Okay, yeah. So that is also, but I want to know like if we check this from like in a, like for any given line, let's say y equals to mx.
Hmm.
So I want to know like if there is 1 by m if coming as a output, let's say for a limit. So is it still because it's still dependent on m, right?
Yes.
Because if 1 by m, so
Hmm.
by that thing also we can say it's limit does not exist.
Yeah, correct. Yeah.
Or even if like 1 by x is coming there and x is tending to 0, and then also its limit
Yeah, it's going towards infinity. So in that case also limit doesn't exist, right?
okay.
So
Okay, sir.
that is also you basically in one variable also when limit tends to infinity, in that case also you say that limit doesn't exist, right?
Right.
So here also the same logic. Like if you are getting limit xy tends to 0, 0, 1 by x, so this goes to infinity. So in that case also limit doesn't
Does
exist.
not
Okay,
exist.
but the thing is, okay, so what I was trying to say, suppose if you take y equal to mx, okay,
Yes, sir.
and by applying the limit, suppose for all y equal to mx, okay, by applying the limit, if you are getting 0, okay, from
Yeah.
there actually you can't conclude anything. Okay, you
Okay.
can't say that limit exists.
There
Okay.
cannot. There can also be some other line or some other curve where it is.
Correct. So for example, there can be some different path. Okay, so if you are coming to 0, 0, you can, let's say, you can come using this path. Okay, let's say this path, and which is not a line.
Okay.
So this sort of procedure helps when you are trying to prove that limit doesn't exist. Okay. So
Oh,
when you are trying to show that limit exists, then certainly this is not a correct way to start the question. Okay.
okay, sir. I get it.
Yeah. Okay. Any other doubt from this part?
Sir, I have doubt in 9.4, but don't know like if you have taught that part yet. It's question number 4. If you can explain it right now, maybe later on when you explain that part.
9 point.
Question number 4 in same activity 9.4. I'm not able to solve this limit actually.
You just need to subtract it. That's all, I guess.
So like we can directly subtract the equation in this, or first we have to subtract the limits of the individual fx and
No,
f and g.
first you need to subtract f of x and g of x. Okay, then you apply the limit, because if
Oh,
you
means directly we can subtract the equation, like for fx what's the equation given, and for g what is the equation given, we will just
yes
subtract it.
yes first you subtract it. Otherwise you may not get limit, because limit yeah. So if you subtract it, then only actually this limit extends x comma y tends to 1 comma 1 will not create any problem.
Okay, I was trying to do it individually, like first limit for f and then limit of g and then time subtracted. So I was
No,
not
so
getting
so
any
so the problem is, see, if I take limit x tends to 0, 1 by x minus 1 by x. Okay, so
Yeah, I get it.
yeah, so you can't get the limit if you apply individually, right?
Yes.
So but if you first subtract, then what you'll get, you'll basically get 0, right?
Okay, sir, I get it. Thank you, sir.
Yes. Yeah, so whether this part is clear, any doubt from this limit? Or maybe I will try to take a question in which limit actually exists.
Yes, sir, that would be helpful. I mean, how to find actually if the limit exists. I mean, the way.
So again, like most in this, there are multiple ways, but in this course, mostly you will deal with one particular method. Again, like this is more or less.
So can you take example with square roots and
Square root.
yes, sir. Like in the denominator using the square root.
It's depend. Like for that, I have to know whether the limit exists or not. Okay. Then probably I can take some examples.
Like anything would be fine if a limit exists or not. It does not exist.
Yeah, then probably if I take square root, then mostly I can easily create some example for which limit doesn't exist. Okay. But okay, before that, let me take this one.
Oh, okay, sir.
If this is 0 comma 0, so I guess this is one of your activity question. So the most standard method that basically you have to apply in this course is sandwich lemma. Okay. So anyone wants to help me how to solve this question? So what I want to do, I want to find the limit of the function at 0 comma 0.
So it would be like x square would be less than or equal to x square plus y square.
Correct.
Sum of x square plus y square.
Yes. So you know this please mute yourself, like whoever is talking. So this x, it doesn't matter what this x is, it's always greater than or equal to 0, and it's strictly always less than or equal to x square plus y square, right? And if I divide this x square by y square on both the sides, of course that I can divide only when this x comma y is not equal to 0 comma 0, because in that case I can't divide because I'll get 0. So what I want to find the limit of this function, right? So what I'm getting here, x square divided by x square plus y square. Still this y square is missing in this expression. So what I can do, I can multiply y square, right? And you know this y square is always positive, right? That means this will not, if I multiply this on this inequality, then it will not change the sign of this inequality, right? So this I'll get x square plus y square divided by y square, right? So now you can see if I take this limit, comma 0 comma 0 0, of course by sandwich theorem you can write that this inequality preserves the limit. right? So this limit is certainly 0, right?
Yes, sir.
Because I am taking a 0 function. Right? So this limit is 0, and this x comma y tends to 0 comma 0. So this function is completely independent on x. So instead of writing x comma y tends to 0 comma 0, I can simply write this is precisely same as y tends to 0, right? And if y tends to 0, so of course, because if x comma y is going to 0 comma 0, that basically means y is also going towards 0, right? So in that case, this limit is also 0, right? So the limit of this function is basically it's in between 0 and 0. That means the limit is 0, right? So yeah, so this is more or less the standard way, at least in this course. There are a lot of probably you can use some polar coordinate argument as well, okay? But in this course, mostly whatever question is there in your activity as well as in graded or practice, mostly you can all the question you can solve by using using this method. But again, you have to slightly modify this argument. Okay, so yeah, uh, huh. So this is there any doubt from this proof?
No, sir.
Okay, fine.
Excuse me, sir.
Mhm.
How are we going to solve the first question? There is a minus in the denominator.
Which one?
First question from activity 8.4. 9.4, sir. Sorry.
Minus in the denominator means y square minus x square.
Yes, sir.
So, okay, so right, this is precisely is the function in the denominator, right? Y square minus x square.
Yes, sir.
So you can use your additive property, right? 2 comma 3 y square x square, right? And what is this limit? What is this one?
So this will be 9.
9 minus 4, 5.
Okay, sir.
Yeah. Okay. So this is more or less the idea of computing limits, and similarly you can. So once you know the limit, then continuity, as I said, it's the same idea. Okay, you just need to check whether the value of the function matches with continuity or not. Okay. So is there any other thing you want me to discuss, or shall I start taking your questions?
Sir, yes, actually you asked if someone else has any doubt in that question. This x square y square upon x square plus y square. So
Sorry,
the
sorry.
last step which you have done, yes sir,
This one.
yes sir, the last step you did, directly evaluating it to 0, I couldn't understand that. We still have it upon in
I
0
can't.
plus 0 form.
It's not clear. Your voice is not coming.
Okay, so just I'll type the message. If you like, you can look at the message in a couple of minutes.
Yeah. Okay. Any other thing you want me to discuss, or shall I start taking your questions?
So one square root example. I mean, anything, as you said, like you can prove it for like the limit doesn't exist. So any square root function, if you can take it.
Oh, just the above you gave, sir, in that you can use the square root in the denominator.
You are saying this one.
Yes, sir, and the square root in the denominator.
Okay, let me try.
It's x squared y squared.
Correct. So this is your function, right? This is again like this is not equal to 0 and this is 0. If this is not equal to 0, 0, right? So again, I guess in this case also limit exists. Okay, since this exists in this case, okay. Most likely limit again it exists here as well. So how I can yeah, so yeah, so the thing is again, so if you go back and see, so when I'm taking the limit at 0 comma 0, right? So the what it doesn't matter what path I am taking. Okay, so the only thing which is actually relevant on this path is precisely it's a small neighborhood of 0 comma 0, right? So it's basically depends this path on this neighborhood. Okay, so if I consider, let's say if I strict, so if I consider, so here let's say I'm taking 0 comma 0. So if I consider this ball, okay, this circle, x square plus y square equals to 1. So if I pick any point inside the circle, then this will satisfy this condition, right? A square and b square is less than 1, right? So it doesn't matter if I considering a path, it doesn't matter how this path behaves outside of this circle. Okay, it's basically what basically matters how the path behaves this near to this point 0 comma 0. Okay, in some in some sense this inside this circle. Okay, so inside this circle uh, your x and y, right? X and y, they're less than or equal to 1, correct? Correct or not?
Yes, sir.
Yeah. So then what I can do, I can write, so x power 4, right, is less than x square,
Yes, sir.
correct?
Yes, sir.
So that
Yes, sir.
means x, because see if x is, so as I said, x is basically in between this interval 0 comma 1 closed interval, right? So if x is a fraction, then if you take the if you take increase the power of x, then the value will decrease, right? So x power 4 is less than y square, sorry, x square, and this is greater than equal to 0, and then I can write this as well, right? Because I'm just adding something. Okay, so now you can see how now it's more or less clear to you, right? How to deal with this function, right?
And then we are going to do the y raised to 4 multiplication, and then we are going to take square root.
Correct. then you take the square root. Okay.
Sir, on the right hand side, it would be y square, y raised to 4, isn't it? Sir?
Yeah,
Instead
yeah.
of 1.
Correct. Yes. So then you take the square root, and next you apply Sandwich limit. So if you apply, then finally what you will get, limit is 0, right? Is it clear?
Yes, sir.
Yeah.
So, no, I have a doubt. Like in the denominator or in the middle, we are going to take square root. So, what are we going to do on the right hand side?
It doesn't matter what you are actually taking. So you take square root on both the sides, on all the sides, right? Square root is an increasing function, right? If a is less than b, right, square root of a is less than square root of b, right?
Oh, yeah, I got it. Sorry. Like in the middle term, we are going to take it whole square root. Yeah.
Yes. So if you take the square root, so what you will get?
So it would be x square y square and then divided by the square root of this.
So this is under the assumption that x square plus y square equals to 1, right? Everything we're doing.
Yeah. So as I said, see, again, under the assumption means what? It's not assumption. It's actually it's enough for you. As I said, when you are taking the path, okay. So when you are taking a path, right? Suppose you are taking a path. Suppose this is this 0, 0. You are taking a path, right? So it doesn't matter actually how this path behaves here. Okay. It doesn't matter how the path behaves here. Okay. How weird this path is here. It doesn't matter. The only thing it matters how the path behaves in a small neighborhood of 0, 0. So in particular, I can choose a neighborhood of 0, 0 in which the value of x, y is less than or equal to 1. Okay. So in particular, what I have done here, I have taken a circle. Okay. So when I'm taking a path, okay, I'm only concerned about this one. Okay.
Okay, so we are just simplifying our calculation because
exactly.
we are only concerned with area around the, like, how the approach is actually happening.
Yeah, it's basically how the curve behaves inside this circle. Okay, that is actually really matters. Okay. It doesn't matter how the circle behaves outside of the circle, outside of how the curve behaves outside of the circle. Okay.
So, sir, if it is like in the denominator, if it's like x square minus y square, then still same way.
I guess still you will get the same limit. Okay, x square minus y square. Still, I guess it will not create any problem. But I don't think the same argument will work. Okay. At least the way I have done here. If I take
if we take
x square minus y square. Then again, we have to be carefully at that time. So the thing is, again, like, see, so when actually you are taking x square minus y square square root, okay, so many times it can be negative. Okay.
so domain would be restricted.
Yeah. So in that case, the domain will be restricted. So you have to be careful actually which path you can choose and what is the domain. Okay, the most crucial part is what is precisely domain. So you have to take the all the points where actually your x coordinate in some sense is greater than. Again, I don't think that also you can say if this is positive. Yeah. So basically you have to take. So when you are taking this x square minus y square, basically 0. Yeah, so basically you have to take all such points for which your x square is always greater than y square. For example, you can take what, -2, 0. Okay, this satisfy the condition, and when you are taking that thing, then you have to be very much careful about the path you are taking. So certainly this proof will not work. Okay, that because here in some sense what we are, our domain is basically R. Okay. So here the domain is not whole real line. Okay, so the domain is all such points for which your x square and y square, x square is greater than y square. Okay.
In such cases, how should we choose the path, sir?
No, so again, see, the thing is, if so, as I said, so most likely, okay, let me try. I'm not sure if I can prove it. No, if you want to show that limit doesn't exist, okay, then you have to choose a path. So here we are actually not choosing any path, right? Here what we are
Oh, yes,
doing, we are
sir.
actually proving the limit exists. Okay, so when you have to show that limit doesn't exist, in that case you have to actually start with two different paths, and for two different paths you have to show the limits are different. Okay, in that case you can show that the limit doesn't exist. Maybe let's say this example, say you are saying what, x square y square.
Y square divided by the under root of x square minus 1 square.
Okay, so this is of course when x square is strictly greater than y square. Okay. And you
It
define
can be, oh, it cannot be equal now, sir.
if it is equal, you define. Okay, so maybe otherwise in what? In otherwise it's, let's say it's 0. Okay. Yeah. Okay, certainly, like, yeah, so mostly you can so in these points actually you can show that the limit doesn't exist, but again you have to be very careful. So you have to very careful. X square is greater than y square, can I get a path? Can I reach a path? No, certainly I can't reach in a path where x square is less than or equal to y square, because if it is coming,
If we take something like by x divided by something, then y would be less
just a
than.
minute, just a minute. I'll ask you, just give me. No, I said right. So here, so if I consider a point, okay, where a square, where a square is, let's say, less than or equal to b square. Strictly less than b square. Okay, in that case actually the limit exists. Okay, so if I consider, at least I can see it. Okay, if I consider this one where a square is equals to b square. I don't think here limit exists. The only portion left is this one. Yeah. Now, what you were saying? Hello.
No, sir. I was just thinking of example or path to satisfy this equation x square is greater than y square.
No. What I'm trying to do, I'm actually trying to find the limit of this function in these points. Okay.
Yes, sir.
Right. So I'm not sure, like if whether I can do it very easily. Because if certainly, yeah, if limit exists, then probably why? Yeah. Limit mostly it's exists because here actually the power is in some sense it's 4. So the below the power is sort of, if you take the square root, it more or less is degree 1. Okay. So above is degree 4. So it will approach to 0 much more faster than the thing whatever is there in the denominator. So eventually it will go to 0. But the question is how to prove it. Any idea? Anyone?
No, sir. I'm still thinking. Like,
X square is greater than y square.
So where the x and y smaller than 1, in those cases then x square will approach 0 slower than x to the power 4.
No, are you talking about which example? This example or the previous one?
Oh, I was talking about this example.
Tell me.
When we have x and y smaller than 1, then x square will approach 0 slower than x to the power 4.
Correct.
So in that case, the numerator being at double the power, it will approach 0 faster than the denominator.
That is fine, but okay, I want a mathematical proof. See, here it's more or less clear that this numerator will approach much more faster to 0 compared to the denominator. But the question is how I can prove it. So here actually I'm proving something, right? It's the whatever I have written here, it's a proof. Okay. This sort of argument, yeah, it's it will help.
Within the limit you have taken, that it itself is a proof that you have taken the limit. You have limited the range to 1. So less than 1, then it is a fine argument itself.
No, if which one?
If you have set the boundary of x and y as less than 1, but it is less than equal to 1. In case it is equal to 1, then it is not valid, but less than 1 will definitely hold.
I don't know what you are talking. Okay, let me take, this is x power 4 x square All right, so then what you do, take minus y square x power 4 minus y square, and you take x square minus y square, and if I take the what if I divide it, what I will get is basically y square minus y square, and then this is x power 4th x square minus y square. This is y square divided by x square minus y square, and this is 1, right? And the next thing what I need to do, I need to multiply what?
So I think the center one will become x to the power x square plus
Just a
y square.
minute. Just a minute. This is y power 6, right? Just let me know if I am making any mistake in the calculation.
So the center one, I think it will become x square plus y square.
Which one?
Sorry, I thought it was x to the power 4 minus y to the power 4.
Right? So what you do now, you add this thing y power 6, this thing. So in that case, what you will get, this is 0, right? So I am adding this. Okay, so I made a mistake. Okay, so I guess you are not listening. This is y power 4 plus y power 6 x square minus y square, right?
Yes.
So now, if you take the square root, right? So if you take the square root, what you will get? It's basically 0 and our f of x, right? If I take the square root, I'll precisely get the f of x. And here, I'll get the square root of this thing. Okay, y power 4, then y power 6 x square minus y square, right? So if I take x comma y tends to 0, this will give me 0, right? The only problematic part is this one, right?
Yes.
So this is 0, right? As if x comma y tends to 0, then y power 4 is 0, right? This goes to
Yes.
0, right? So I can simply ignore it. Okay, so instead of considering the whole thing, I can simply take, let's say, this one. Right? I can simply take this one. So, and again, so suppose, so now what I want to do, I want to compute the limit of this function. How I can do that? Any idea? How I can find the limit of this one?
Taking y square common.
Y square common. So then what will happen? Y power 4 minus 1. So then it's not going to help.
So what I can think is only polar coordinate issue over here. I mean, if we apply that r cos theta, r sin theta, I think that would be helpful for this specific problem.
Yeah. So the thing is, yeah, polar coordinate. If you apply, then you have some r power 6, and yeah, so we'll have cos square theta minus sin square theta 1 by this, and you have r power 4. Okay. So, and then this is probably, this is cos 2 theta, right? Cos square theta minus sin square theta, what is it?
Cos 2 theta, yes, sir.
Cos 2 theta.
And yeah, if you take, it will basically you will get 0. Okay, so that is fine. But again, like you don't have all these things in your course. But I want to try. I want to do it directly. Okay, so the main idea, actually, not idea. So I was trying to prove by this sandwich lemma. But again, I'm not sure if whether I can apply the sandwich lemma here. Okay, because I certainly I don't see any direct method for this one. So only thing I can do, I can come to this this place. Okay, and again, for here also I have to deal with this one. Okay, because dealing with this one is easy. It's just y power 4. But this one I'm not sure. Still, I'm not sure how to tackle this one. This is, I don't think it will work. Any idea? Otherwise, I'll stop here. Okay, because I don't want to continue it further. I'll try to see whether you can do it by applying sandwich theorem or not. But probably I'm not sure whether you can do it. But if you can do it, then probably I have to spend slightly more time on this. Okay.
Oh, it's okay. So otherwise, the polar thing is fine over here.
No, polar, as I said, the polar you can do it. Okay, so polar is not a problem. But again, see, polar is not in your syllabus. So I wanted to do it using sandwich, but I don't see this minus sign. As you can see, it's creating problem. Okay.
Yes, sir.
Yeah, you can't. This is actually creating problem for you to apply the sandwich lemma. So here the only thing, why, because of this plus sign, actually you can apply easily this. You can easily get this inequality, and after that you can apply the sandwich lemma. Okay, still I'll try to find a solution for this. Okay.
Okay, sir.
Yeah. Okay, anything else you want me to discuss? Activity? Any doubt from activity part, or like you have solved all the questions?
So one question, I cannot remember the number, so I'm just trying to find the question.
Okay.
Okay, sir, found it. 9.3, ninth question. I'm not getting minus 20 actually.
What is the answer? Minus 20.
It's minus 20, yeah.
You have basically you need to find the directional derivative, right?
Yes, sir.
Let me take the write the question. So you have a e power minus x square plus y square
minus 4z square.
4z square, right? And what you want to find the rate of the change of the temperature at this point along the direction of this one, right?
1 minus 1 and
okay, so how you can do it?
So I use the gradient rule. I mean, partial
Gradient.
derivatives, found the gradient, and then multiplied it with the unit vector.
Okay,
I mean, the directional unit vector.
So if you take the so that is probably the easiest one, because if you take the derivative, you have to do a lot of like the if you go through the
So
definition,
it's a lot of calculation.
Yeah, you
it's
have
a lot
to
of
do
calculation.
So no, you should get so if you are doing, just a minute. So if you are computing what is the partial derivative of this function with respect to x, so this is 10 this is minus 4z square, right?
yes, sir.
Times minus 2x, right?
Minus 2x, yeah.
Minus 2x, yes, sir. And for rest also it like the same term, and then into 2y with respect to y.
Into 2y, correct? And the same thing times
minus 8c.
Yeah. So now what you need to do, you need to evaluate this one at 2 minus 1 0, right? So this becomes 0, right? The third coordinate is
yes, sir, is 0.
The first coordinate is 10 minus 40, right? Correct?
Yes, sir. 2 into 2, 4.
Minus,
yeah, minus 40.
E power
minus 3.
Minus 4 minus 3. Yes, correct. This is again minus 20, right?
Yes, sir.
And you have 0.
0.
Yes. and you have 0, right? This is your gradient. Gradient of the function are 2 minus 1, 0. So the next thing what you need to do, you need to multiply with the unit.
It's 1 by root 3.
1 by root 3.
Minus 1 by root 3 and 1 by root 3.
So if you take, what you will get? Minus
40 divided by root 3e minus 3. And then plus 20, we will get some plus 20. So answer would be minus 20.
And now I can see where did I make a mistake. Okay.
This multiplication, right?
Yeah, that one.
Hmm.
I actually, sir, I altered the sign. I just saw it when you did it. So I was just telling it with my answer as well. So okay, got it, sir.
Yeah.
Thank you.
So okay. So anything else from the activity part?
So, sir, I mean, a normal thing. I just want to ask you. I know you have said it before, and I know you're gonna say it again, but still, I just want to ask you that. I mean, if the limit does exist, then the pathway is not a viable way to prove it. We have to prove it. We have to prove it, right? The way you proved earlier.
Yes.
Okay.
So the thing is how. So if you take, see, if you take not sandwich is not the only method. Sandwich is probably the only method through which you can solve all the question for this course. Okay, so there are multiple. See, the problem is, see, if you take some thousand number of paths, okay, and for 1,000 number of paths you are getting the same limit, right? But still it doesn't matter, right? But still it doesn't matter because there are infinitely many paths. Still you missed infinitely many paths, okay, and for which you didn't compute the limit. Okay, so when you are when actually you are trying to say that limit exists, then taking multiple paths is not a correct way of solving the question. So you have to prove it. Okay, you have to give a proof.
But sir, another thing, I mean, do I have to prove it using the sandwich theorem? Because I'm pretty I mean the polar coordinates actually go easy on me, so I can use that theorem as well.
Okay, so again, right? So the problem is, okay, so the polar coordinates actually you can apply, but sometimes actually polar coordinate also fails. Okay, so you have to be very careful.
Okay.
So you can't apply polar coordinates everywhere. Okay, and sometimes if you apply even polar coordinates, it will give you the same limit, but still the limit doesn't exist. Okay, there is a as I know some condition on the function. I don't remember what condition, but there are some condition on the function. On those cases, if your function satisfy all these conditions, then only you can apply the polar coordinates. Okay. So
okay.
So some, again, like occasionally the polar coordinate method also fails.
Yes, sir. If the denominator is having higher degree, then I guess that won't help polar coordinates.
So again, like, see, as I said, so the checking limits for multivariable function is really difficult. Okay, so you have to be very careful. If I slightly change the function, then it can create a huge problem. Like for many cases, there are many functions for which if you take this one, if you take this path, it will always give you 0. Okay, if you take this path. But for example, if you take some kind of path like this, okay, and some path like this, okay, then probably it might help you, okay, to show that limit doesn't exist. So there are various type of functions. So you have to be very careful when you are trying to find the limit, or you are trying to show that limit doesn't exist.
Okay, sir, got it.
Okay, anything else? So I don't. If you don't have any question, then probably I'll stop now.
Sir, in the quiz 2, we have the syllabus till week 8, right?
Week 8, yeah.
Week 5 to 8 would be more of a focus.
Probably week 5 to 8, yeah. So I actually I'm mostly I am not sure. I have to check the question. So I can tell about maths 1. Still now I didn't see the question of maths 2. Okay, but yeah, most of the questions certainly will come from week 5 to 8. But again, to solve the question of week 5 to 8, you need the concept of vector space and all these things.
Yes, sir.
So mostly focus will be on, I guess, week 5 to 8. Okay. Again, I have to see the question, then only I can give you a correct answer.
So like even in stats 2, it's this kind of distribution only. So I was just wondering what syllabus and everything you have to say.
Yeah. So probably it's better if you ask Subhajit or maybe Susmita. I still now I didn't see the question.
Okay, sir.
So another thing, I mean, basically, in maths 1, I remember you precisely said that quiz 2 would be the hardest. So is it same for maths 2, or is it like you guys are taking the standard of the quiz 1 paper, then you're gonna set the quiz 2 paper, or is it like same as maths 1? I mean, the hardness, the level of hardness.
Okay, so I guess previously we used to do this thing. Okay, so generally what we do, so we see the result. Okay, so in quiz 1, so usually we prepare quiz 2 question after we see the result of quiz 1. Okay, if you are doing really well in quiz 1, then most likely we increase the standard of quiz 2. Okay, and if most of the students are doing really bad in quiz 1, then we decrease the standard of the question. Okay, so but nowadays what we do, you prepare all the question question in the beginning of the semester. Okay, so now we are not following that method. Okay, so as I said, so you said right. So usually we increase the level of the question. So previously we follow this method. Okay, as far as your result, we similarly we try to balance the question. Okay, but nowadays we are preparing the question in the very beginning itself. So now you can't say anything about the standard. Okay, it's completely independent. Okay, it's depend who is preparing the question. Okay.
So, sir, since you haven't seen the question paper, so you cannot, I mean, you cannot give us an overview like what to expect or something.
Yeah,
I mean,
yeah.
I'm not asking you to tell everything. I mean, you know, like
No, sorry. I didn't see the question. Okay, so you probably it's better if you ask Subhajit and Susmita. They can give you better.
Okay, sir.
Yeah. Okay. Anything else, or otherwise I'll stop the session.
Sir, like in every open session, we cover the entire thing, right? We cover the theory aspect. So if we want to revise, we can just review in the open sessions.
This is okay. This so in open session, they revise all the concept. I don't.
In statistics, sometimes they revise the.
No, I'm talking about maths too.
Yeah, so maths too. I was saying also because I have not attended many open sessions, so I.
Okay, so I have questions. Whether they revise the concept in open session in maths too?
Yes, sir. They do. I mean, it depends who the instructor is. I mean, Shushmita ma'am and Shubhajit sir actually do that.
Okay.
And then they ask for doubts and all that.
Okay, I don't know. Like so. Okay. Actually.
So I've also not like seen the lectures, but like I am when you were explaining, I was able to understand everything.
No. So the thing is, okay. So the thing is, okay. One actually, usually I don't take session in maths too. Okay. So as far as I remember, I took one session, open session. Actually, Subhajit told me you don't have to revise the concept. So that's why I'm not revising the concept. Otherwise, I can also revise a few concepts. Okay. So let me start revising the concept. Okay. So okay. So let me start with the from the beginning itself. Okay. So I guess this this may be boring for some of you. So first tell me what is hello, what is scalar valued function? Any idea?
When the function is defined from Rn to R, it's
If it's a function d to r,
R square. Yes, sir.
where d is a subset of
D is a subset of
Rn.
rn,
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 sir.
sorry. Yeah,
and
Rn.
there is a condition on n, right? Where n is greater than 1, right? So when you have a function from a domain, okay, so there is a different meaning of domain, but okay, so for here you think d is a subset of this Rn. So if Rn and n is greater than 1, in that case you say that your function is scalar valued multivariable function. Okay. So okay, so the obvious example is your linear transformation. So you can take this linear transformation, let's say R3 to R, and what is your map? X, Y, Z,
Z equals to X, Y, Z.
X plus Y plus Z. Right. So this is a linear transformation, right? So it's a map from R3 to R3. Sorry, R3 to R, and as you can see, your n is greater than 1, right? And it's nothing special about linear transformation. You can take any arbitrary map, let's say R to R, where x comma y goes to x square minus y square. Okay. So this is also a scalar valued multivariable function. Okay, and so mostly you have two types of function. Okay, so one is scalar valued multivariable function, and the another one is vector valued multivariable function, right? So can one of you tell me what is the definition for vector valued multivariable function?
And the function is defined from Rn to Rm, where m and n are greater than 1.
Correct. M and m comma n. Sorry, this is not Rm. This is Rn. M comma n is greater than 1, right? So again, you can take some linear transformation. Let's say R3 to R2. Any example of linear transformation from R3 to R2?
P of x, y, z equals to xy plus yz. Oh, sorry, sir. xy comma
XR.
yz.
Uh,
xy comma yz, sir.
Xy comma yz.
Yes, sir.
This is a linear transformation.
it's not actually
No,
X
sir.
y
X
comma y
plus
plus
y,
z.
y plus z.
X plus y plus y.
X
Sir.
plus y
Z.
plus z.
It can't have more than.
Yeah. Okay, so this is a vector valued multivariate function, because here this is your n and this is your m, and both m and n are greater than 1. And similarly for there is nothing special about this linear transform. You can take any arbitrary map. Take this one, let's say x comma y goes to e power x, e power y, e power x plus 1. So this is a map from R2 to R3, and here both m and n, they are greater than 1. Okay, so this is an example of a vector valued multivariable function. So in this course, what so particularly in week 9 and 10, so mostly, and 11, mostly you will deal with scalar valued function. Okay, so dealing with vector valued multivariable function is slightly trickier and as well as difficult. Okay. So the first thing what you study for a vector valued multivariable function. So similarly, what you have studied for single variable function, you can always add and you can multiply, you can compose all these vector value. You can add, multiply, and compose all these scalar value multivariable function. As I said, we are not going to deal with this kind of function. Okay, so yeah. So you can add. So how you are going to add this function? Again, it's component wise. Right? And you can similarly so again, like
scalar multiple and
yeah. So yeah, so this you can scale and multiply, but again, this is really, it's a bad, in some sense, a bad definition. And if g of g is non-zero, then you can as well as define the quotient, right? Again, with respect to the condition that g is not equal to 0, like yeah. So because if g is if at some point g is 0, then this is not well defined. Okay, so the next thing what you do, so when you studied function of one variable, you basically studied the derivative, right? So there actually you have only one so you have only one variable, right? So you consider a function from R to R. So this is a one variable function, right? So what you study when you have studied derivative for a one variable function. So what basically derivative gives you?
So the rate
Instantaneous change.
Sorry?
Instantaneous change. Rate of.
Correct. So basically what? So if you are suppose you have a function, right? Suppose you have a function. So the derivative, in some sense, if you take the derivative, it basically gives you the slope of the tangent line, right?
Yes, sir.
And this slope basically decide how the function behaves at that point. Okay, so as someone said, it basically tells you the instantaneous change of the function. Okay, so similarly you can do the same thing for a multivariable function. Okay, but here now, so when you consider a multivariable function, so now you don't have a single variable, right? So here you have only one axis. So the domain is basically your line. But when you are considering a two variable function, here you have two variables. Sorry, here you have basically two direction. Not two direction. You have two variables. So this is your y, and this is your x, right? So you can talk about the derivative of the function with respect to y, right, and with respect to x, right? So if you go and check the definition of differentiability in a one variable function, what actually, suppose when you say that f is differentiable at a for a one variable function, if f is a r map from r to r, then how you define?
When it is continuous.
So if it's continuous, and if the left hand derivative and right hand derivative are equal at that point,
how you define it? Limit s tends to 0.
f of a plus h minus f of a by h.
H, right? So if you consider this line, this is your point, right? And in some sense, actually what you are doing, so this is your whole space. Okay, so this line is precisely the universal space when you are considering a map from R to R. Okay, so what you are doing, you are actually going in this direction, and you are going in this direction. So that's why you are just applying a plus h, right? So this h is a real number, right? But when you are dealing with a two variable function, right? So when you are talking about the derivative, okay, with respect to x, so this point is what? X comma 0, right? Right or not?
Yes, sir.
So now,
yes, sir.
So now if you want to reach to this point x comma 0 by using this x-axis, right? You can use this x-axis from the right hand side as well as from the left hand side, and also like from this angle as well. But we are only concerned about the derivative with respect to x. So we'll stick to this x-axis. Okay, so this, since now I'm in this plane, this h, so I have to replace this h by what? H comma 0.
Yes,
right?
sir, because it's a plane.
Right. So what I have to do now, I have to take limit s tends to 0 f of x plus 0 plus s comma 0 minus x comma 0 divided by h, right? So this is nothing but what? Limit h tends to 0 x plus s times this right? So in case of two variable, this is the partial. So instead of using word derivative, this is the partial derivative of the function f at where? At which point? At x comma
X
0.
comma 0.
X comma 0.
At x comma 0 with respect to
X.
right? And again, so in some sense, nothing special about this point x comma 0. So why basically I have taken this point? So to show some analogous between this r square and r. Okay, so you can, instead of taking x comma 0, you can use any arbitrary point. Okay, so instead of x comma 0, you can take any arbitrary point a comma b in your r, and in that case the partial derivative of the function at this point with respect to x is what? Limit s tends to 0 f of a comma b by h. Okay, so what it's basically saying, so if you take the point, let's say this is your 1 comma 0, and let's say this is your a comma b, right? So what this thing will represent? Anyone? What this thing will represent? What is this? If I vary h over r, what is this?
Sir, we have increased it by a small value h.
Sorry?
We have changed a comma b by a small value h.
But only
Moving
on
the point.
x.
So it's the rate of change along the direction 1 comma 0.
Correct. So no, yeah, that is fine, but I'm asking about this one.
This is change of x coordinate
You have
in
studied,
direction of 1 comma 0.
you have studied in week 8 what you have studied? Inner product, right? Then what about week 7? You have studied some affine space, right?
Sir, affine transformation and affine mapping.
So
yeah.
what I'm asking, what this set will represent?
The subspace. Of R2.
See, I'm asking what is this set A? A, B is a fixed point, right? And I'm taking this one, s comma 0, right? Where h varies over r. What is this set? What this set will represent?
So with variation value of h, it will move along the x-axis a comma b.
Okay, so before that, tell me what is this one? What is this?
It's a support point. I mean, if
Not
you're talking about
not support
affine
point.
mapping, then it's a support point.
You just tell me what
X-axis.
this is what? This is span of 1 comma 0, right?
Oh
Yes.
yes.
Thank you.
So that what basically this is x-axis, right?
Yes, sir.
Correct or no?
Yes.
Yes, it is.
And now what you are doing, you are just adding a comma b in this x-axis, right? So that means what? This is a affine space, right? So what you are doing, you are basically translating this x-axis by this point a comma b, right?
Oh yes.
So in that case, what you will get? Right?
So parallel line to x-axis.
Right? Yeah. So now actually what? So when you are taking this thing, right? When you are taking this thing, whatever it is, okay, you are basically you are computing in some sense the partial derivative, right? At the with respect to x at the point a comma b. So what you have this function, right? You have this function. This is whatever it is. It's a map from R square to R, and you have this line. So this is your AB, and when if you take h towards 0, then this is more or less you are basically in some neighborhood. Okay. So when you are computing the partial derivative, okay, at point a comma b with respect to x, it's giving the behavior of the function, okay. As someone said, in case of real variable, it's giving the instantaneous change of the function at that point, okay. So it basically for a multivariable function, this notation, okay, whatever it is, it basically gives you the instantaneous change of the function in this region at basically at the point a comma b, okay. Of course, along this direction, right? Along x-axis, because there are infinitely many lines which passes through this point, right? So okay, so let me take, for example, let me draw 3D diagram. Okay. So right, so suppose this is your graph, okay. So when I'm talking about this point a comma b, right, and let's say I'm talking about the change with respect to x-axis, right? So then what basically I'm checking the value of the function, the behavior of the function along the x-axis, right? So if I consider, instead of this one, if I consider, let's say, some other, let's say y-axis, right? So then what I have to do, I have then basically this the limit s tends to 0, instead of f of a comma b, I have to consider 0 comma, right? So in that case, this limit will give me some information about the behavior of the function in this direction, right? So the direction matters, right? So what direction you are choosing, that matters, okay, because now you are in 3D, okay. So when you are taking this line, okay, this will give you the change in this direction, okay, and the function can behave completely different in this direction and this direction, okay, because direction matters. As I said, you are in 3D, so your domain represent a two-dimensional plane, Okay, so when you are taking the derivative with respect to x-axis, then it's giving you the information how the function behaves in this direction. Okay, at this point a comma b, this is f of a comma b. Okay, in this direction, and with respect to a y-axis, this will give the information with this direction. Okay. Is it clear what basically we mean by this partial derivative?
Yes, sir.
Okay.
So-
Hello. Hello. Okay. So, any questions related to partial derivative?
Yes, sir.
Hmm.
So we are saying that I can see that if this limit has we are adding h multiplied by 0, 1, so only it will move along the x-axis.
This is
But-
along x-axis. Yeah.
Yes.
Hmm.
So we can define it for both the axes any
Yes.
way we want. But in this particular case, we only have it only moves along the x-axis.
Yeah. So here this definition is basically with respect to x, right? I said, right, this basically represents the derivative of the function with respect to x. Okay, and similarly I can define the derivative with respect to y as well, y as well. So for that, what I need to define? So what I need to define? See this. What is this y-axis? This is basically 0, 1, right? So when you are considering, so when you want to find the behavior of the function, okay, at a point with respect to y-axis, okay, so then what you need to take? So if you take a point a comma b, and you want to find the the behavior of the function at this point along y-axis, that means what? You are considering this line, right? So
Yes,
what
sir.
basically this represent? A comma b plus h times 0, right? So in that case, similarly you can define this is as limit h tends to 0, a comma b plus h of 0, 1 minus f of ab by h. And again, so there is a concept of directional derivative. So there is nothing special about this x-axis and y-axis. So you can actually talk about the actually you can talk about the derivative in any direction. Okay. There is nothing special. So instead of why I always have to consider some with respect to x-axis and y-axis, because there are, so if I consider a plane, there are infinitely many directions, right? If I consider a plane, right? If I consider a plane, so this is not the only direction. This is not the only direction. I have lot of direction. This is also a direction. This is also a direction. This is also a direction. Okay. So with respect to all this direction, I can talk about the rate of change of the function with respect to some point, and that is precisely and that's why actually we are computing the directional derivative. Okay. So the directional derivative actually it can tell you the rate of change of the function at a point with respect to any direction.
Thank you, sir. So, sir, with any direction, we need to find the directions because we want to calculate perpendiculars to any direction at orthogonality. Otherwise, okay, and sir, any number of directions we can define it on, not just as x, y, and z3. Thank you, sir.
Okay, any questions related to this partial derivative? Okay, okay. So apart from this, any question from your activity or practice?
So just one thing. I mean, we can use the gradient rule for the directional derivative if the function is smooth. Smooth means continuous at everywhere or something like that, right? I mean, let's say at any point that function is not continuous, so we cannot take the partial derivative and create the gradient and just multiply it with the unit vector, isn't it? I mean, is it right or wrong?
No. So the thing is, okay, so you have to, when you are applying this gradient rule, you have to make sure the gradient, first of all, the gradient should exist, right? So
Yeah.
gradient, see, if you have a function, okay, then when you are computing the gradient is again is another function, right?
Yes, sir.
Right. So this is, suppose if f is a R to R, right? Then sorry, R to R. Then this is your gradient, right?
Yeah.
So then gradient is also a function from R to R. Correct?
Yes, that is true.
So now you can apply this rule at a point, let's say a1 and a comma b. Okay, if this gradient is exist at this point as well as continuous around some open ball of a comma b. Okay, you should find a circle. Okay, and whose center is a comma b, and this function should be continuous on this region.
Okay.
Then only you can apply that rule. Both the things. This partial derivative with respect to x as well as the partial derivative with respect to y. Both the things. If both the things are continuous on this region, okay, then only you can apply that rule. Otherwise, you can't.
Okay.
Probably you have some example where sir actually discussed in probably in your next so you probably it's the video lecture is in the next week. Okay. So you can't apply arbitrarily. Okay, you have to make sure that this gradient is continuous. Okay. So first you have to compute this. Okay. First you have to compute this. Then you have to check whether, so this is a new map. Okay, f is a map. So when you are taking the partial derivative, you will get a new map, a new function, right? And this function should be continuous around this point a comma b. Then after that you can apply the gradient rule. But again, so if you have some see, the main problem is in most of the cases the boundary point. Okay, so for example, if I define a function like this, okay, so some piecewise function is, let's say, x square y square divided by x square plus y square, and if this is not equal to 0, and if it is 0, this is 0. So the main problematic part is this one, because if you take any point apart from 0 comma 0, this is always continuous. Okay, this is continuous, the derivative also continuous. If you take any number of time, so if you take df dy, even if you take d square f dx dy square, okay, whatever you take, this is always continuous at a point around this point a comma b, if a comma b is not equal to 0. Okay, the only problematic part is this one. So for this part you have to check it separately.
Okay.
Okay, any other doubt? Okay, then I'll stop now.
Thank you, sir.
Thank you so much, sir.
Thank you.
Sir.
Thank you, sir.